Hello everyone! We are starting our last section of Chapter 9, Significance Tests. We have learned the basics of significance testing. We have learned how to perform a significance test for a population proportion. And in this one, we're going to do tests about population means. Now, we're going to be using T procedures for means unless we by chance know the population standard deviation sigma, which, let's be honest, that really never happens. Okay? If we did know it, we would use Z procedures like we do for proportions. But again, very rare instance that we would actually know the population standard deviation. This is our general formula that we're using. Our test statistic is equal to our statistic minus our parameter over the standard deviation of the statistic. That's the same for both sections, but it gets more specific for this one when we're looking at means. Okay? So we have our T, and we have our X bar, which is our statistic, our sample mean, minus our parameter, this is going to be our claim mean, over our standard deviation of the sample divided by the square root of the sample size. So what we're going to do is we're going to choose a simple random sample of size n from a large population that contains some unknown mean. To test the hypothesis that the mean is equal to some claim, we're going to compute a one-sample t statistic. Okay, so this is the name of the method, a one-sample t statistic for mean, or a t-test, I should say. Then you're going to find the p-value by calculating the probability of getting a t statistic this large or larger in the direction specified by the alternative hypothesis, remembering that in a t distribution we have to use degrees of freedom, and that's always n minus 1. Okay, so we need to remember that we're using t, so we can either use that table or we can use our calculator and specifying our degrees of freedom. So let's go through an example together. Every road has one at some point, construction zones that have much lower speed limits. To see if drivers obey these lower speed limits, a police officer used a radar gun to measure the speed in miles per hour, miles per hour, of a random sample of 10 drivers in a 25-mile-an-hour construction zone. Here are the results, and we have those 10 data values. If I were you, I would just go ahead and plug those 10 data values into your calculator now. Put them in your list 1. We're going to use them here in a little bit. Is there convincing evidence that the average speed of drivers in this construction zone is greater than the posted 25-mile-an-hour speed limit? All right, so let's work through this together. So just like in the proportion section, we're going to go through our 4-step process using our phantoms acronym to help us remember our steps. If phantoms doesn't work for you, then don't use it. It's just something to help you kind of remember what things are. So let's just go ahead and get started. We always need to start with what we're doing, as in which hypotheses are we trying to test, what alpha are we going to use, defining any parameters in the problem. So we want to test the following hypotheses. It didn't specify a significance level alpha, so we always just assume to use 0.05 unless it tells us. This is a problem about means, right? I know that because it said the average. So we're going to use mu as our symbol for our parameter. Our null hypothesis is always an equal. We want to know if we're comparing it to 25, so they're saying it is 25, but we want to test to see if it's greater than 25, where what is mu? The true mean speed of drivers in this construction zone. Okay. Let's go ahead and go with our plan. So if our conditions are met, we are going to do we're going to carry out or we're going to perform a, what's this called? This is a one sample t-test for means. Please remember to have all three parts. One sample, t-test, for mu. 1, 2, 3. So let's check our conditions. In our random condition, let's see, what did it say in the problem? Took a simple random sample of 10 drivers. So that condition is met. Normal. When we're testing for normality for means, we have to look at the problem and see if it told us that the population was normally distributed. Doesn't say that anywhere. So then we have to look at the sample size. This is a small sample size, guys. It's only 10. As long as it's greater than or equal to 30, we can assume normality, no problem. But because it's smaller than 30, we need to graph our data. You can do a dot plot, you can do a box plot, you can do a histogram, you can do a normal probability plot, any of these things. And so we need to write that and then graph it. So this is why I told you to put that data into your calculator. I'm going to do a box plot here, right? A box and whisker plot, simply because when I do that, it will show me if there are any outliers. And that's one of the things we check for, right? We check for outliers and we check for skew. So in my calculator, I entered in my 10 data values. Make sure you enter them in correctly. Okay. Then I'm going to go to stat plot. I'm going to turn it on. And I'm going to choose this guy right here, right? This is the box plot that shows me if there's any outliers. So I'm going to exit out of there. Make sure there's nothing in my y equals. Plot 1 is on. So then I go to zoom, and we're in stats class, so we always pick zoom stat, which is option number 9. And it gives me this lovely box plot. There are no outliers. It's not perfectly symmetric, but I wouldn't call that a strong skew, so I think we're good to go. Now, I do need to graph this pretty accurately. So if I go to stat and calc and one variable statistics for this list, and I scroll all the way down, I have my 5-number summary right here. So that's what I'm going to go ahead and I'm going to graph that. Okay, so here's our box plot, our median or our minimum, Q1, our median, our Q3, and our max. Right, and I got all of that from my calculator. I labeled it miles per hour. So we can say since there are no outliers or strong skew, we can assume it's safe to use, or I should say safe to assume. We can assume it's safe to assume, that's a little redundant, but you know what I mean. We can assume that it's safe to assume that we are approximately normal here. Okay. So let's go ahead then and do the last condition, and that's going to be independent. This was not an experiment, this was a survey, if you will, so we need to check the 10% condition. So because we're sampling without replacement, we need to check the 10% condition. And we're going to say that it's safe to assume there are more than, let's see, 10 times 10, which is 100. 100 drivers that go through this construction zone. Okay, we're halfway there. So now what we're going to do is we are going to go into the do part. This is where we do our calculations. Okay, so using our formula to find our test statistic t, we take our sample mean minus our claim mean over the standard deviation of the sample divided by the square root of n. Now the problem didn't explicitly tell me this or this. It told me that my claim was 25, and we know that my sample size was 10. But as far as the sample mean and the sample standard deviation, it wasn't explicitly told to us. But we have it in our calculator because we have the raw data. Okay, so our x bar is 28.8. And our sample mean, our S, is 3.938. 3.938. Then we can go ahead and calculate what that's going to be. So 28.8 minus 25, numerator is going to be 3.8. 3.938 divided by the square root of 10 is 1.245. 3.8 divided by that thing gives me a t of 3.051, más o menos. Okay, so now what I need to do is I need to find my p-value. Okay, so in order to do this, I need to know my degrees of freedom. So since n was 10, my degrees of freedom here are going to be 9. Okay? So then when I want to find my p-value, I would know the probability that my t is above 3.051. So I need to use TCDF for this. So I'm going to go to second vars, TCDF. Since I want greater than that, 3.051 is my lower. Some really big number for my upper. Degrees of freedom here is 9. And we get a p-value of 0.0069. 0.0069. Alright. So then we can come to a conclusion about this. Okay? And conclude just the way we did before, right? If your p-value is smaller than your alpha, you reject your null and say there is enough evidence to conclude your alternative. Since our p-value is less than our alpha, we are going to reject our null. So there is sufficient evidence to conclude that the average speed of drivers in this construction zone is greater than 25 miles per hour. Now, remember for the do step, you can write it all out like this. You can also use your calculator to check it. So let's see how we would do that here. If we go to stat and we go over to tests, we have to pick the correct one. So what are we doing here? Well, it's a one sample t-test. So I believe I'm going to do option 2. That seems like the best one to me. Now there's two options here for input. There's data and there's stats. We actually have the data here, meaning that my data is in list 1. The claim was 25, and this was a greater than test. So when I go to calculate it, it tells me all the things. It gives me exactly what I had for t, what I had for my p-value, my sample mean, my sample standard deviation, my sample size. So a great way to check it is using your calculator. Okay? Turn this page and do the example on the back. Next video we'll have it all worked out for you, but I want you to do it first. Okay? You do it first. Good luck!